Good morning. We are going to begin on section 3.5 and learn derivatives of trig functions today. Section 3.5 through 3.9, we're going to be learning a lot of new derivatives of functions that aren't x to some power. And we'll end up taking another chapter test on 3.5 through 3.9. I would say it will definitely focus on 3.5 through 3.9. All of our tests will bring in concepts from previous sections. But we've got a long while before that. I will plan on having your test ready to go over on Monday, but I will see you tomorrow on Friday. All right, so section 3.5, derivatives of trig functions. What we're going to learn first is that the derivative of sine is cosine, and the derivative of cosine is negative sine. So I'm going to give you a minute to copy that down. Okay, so I'm going to say it again here. The derivative of sine is cosine. Now I'm going to ask you, and I want whoever's in there to actually hear you. What is the derivative of sine? What did you say the derivative of sine was? Awesome. So what's the derivative of cosine? That's right, negative sine. What's the derivative of cosine? Negative sine. Great. What you will see or find out is that all the derivatives for the co-functions, cosine, cosecant, cotangent, all of the co-derivatives are negative, and that's kind of nice that they're consistent like that. Now, if you want to see an algebraic proof where or why is the derivative of sine equals cosine, the algebraic proofs are in the book. I'm going to show you graphically why the derivative of sine is cosine. And we've actually already done this a little bit when we did that graphing worksheet. The first thing I'm going to do, I'm going to step away, and remember how my voice gets quieter when I do this, so you might want to turn it up a little bit. The first thing I'm going to do, is graph sine. So when I graph sine, I know sine goes through the origin. Oh, I'm crooked. And then it goes up one, down one, down one. I'll have to reorient this thing. So the graph of sine looks a little bit like this. Okay, that's the graph of sine. Now, this is the graph of sine. If I want to graph the derivative of sine, then I know that any place there is a maximum or minimum, which is right here, okay, that's a maximum, that's going to become a 0 on the number line. So there's another minimum, and it's going to become a 0 for the derivative. There's a minimum, so it's going to become 0. There's a maximum, it's going to become 0. Okay, so there's all the places where there's 0. Now I know from here to here, I'm increasing. So that means that the graph of my derivative is going to be positive. Okay? Then I know from here to here, I'm decreasing, so my graph's going to be negative, and it's just going to switch around. All right? So if I think about that, when I draw the derivatives, I'm drawing slope. I want you to kind of look at what happens to the slopes. Right here, the slope is 0, and now it's like a tenth, and now it's like a half, and then it keeps getting steeper and steeper until we get to right here. It's about as steep as it'll be right there. And now it starts getting less steep. Well, if you think about it, about how steep is it right there? How steep is it? I would have to guess it's, 1. Okay, that's about what the slope looks like. And so right there, right about here, the slope is 1. Okay, so I'm going to plot 1 on there. So when I go to graph the derivative then, and I want to go positive and then negative and then positive, you notice how, holy cow, look what I just graphed. Cosine. So the derivative of sine is cosine. Now I'm going to do the same thing, only I'll graph cosine first. If I go to graph cosine, and I'm going to be a little quicker this time, because we've done this once already, that's sort of a sloppy graph of cosine. Okay? So now if I want to graph the derivative, any place that there is a max or min, I want to do a 0. Max or min is 0. Max or min is 0. Let's see, where's another one? Right here. Max or min is 0. So from here to here, I'm increasing. So that means from here to here, I need to be positive and then negative, etc. And so when I go and graph that derivative, what you'll notice is that it looks like sine, only isn't sine supposed to start at the origin and then go up? This one goes down. And so you'll notice that the derivative of cosine ends up being negative sine of x. All right? All right, so you believe me, you trust me, right? You just need to memorize it, okay? Memorize it. What is the derivative of sine, class? Out loud. 1, 2, 3. What's the derivative of sine? Okay, and the derivative of cosine. Awesome, so you just need to know that. So let's do some examples. We're going to find these following derivatives. Okay, so the first example, we have y equals sine of x plus cosine of x, and I want to find the derivative. So what did you say the derivative of sine of x was? Great, cosine of x. And then what's the derivative of cosine of x? Negative sine of x. So I wrote plus a negative sine of x. Personally, I would just write this like this. That was very, very simple, wasn't it? Okay, easy derivative. Now, if we look at the next one, we have f of x equals x squared cosine of x. Isn't there really a times sign between those two? It's really x squared times cosine of x. So I have two functions multiplied together. So what do I have to use when I have two functions multiplied together? Yep, product rule. I have to use product rule. And product rule says that I take the derivative of one of them times the other one, and then plus the derivative of the other one times the one. So I'm going to find df dx. And what I'll do, I know that order doesn't matter with product rule. You can switch the order of the plus in between the signs. But I'm going to go ahead and do the derivative of the first function first. So what is the derivative of x squared? 2x. And then we take that times cosine x. And then plus, now we're going to take the derivative of the second function, which is cosine of x. And that derivative is negative sine of x. And then we're going to take that times the derivative of the first, times just plain old the first function, which is x squared. Now, I don't like to write it in this order, because doesn't that look like it says negative sine of x times x squared? Do I mean sine of x times x squared, or do I mean sine of x times x squared? I really want the x squared times this whole function, so I'm going to write this in a different order. I'm going to write it as 2x cosine x minus x squared sine of x. I'm going to write it like that. That's just better form. Okay? All right, the last example is y equals x over sine of x plus cosine x. What rule am I going to have to use here? Yep, quotient rule, because we are dividing. So if I want to find the derivative here, I'm probably going to run out of room. Actually, I think what I'll do is come over here. So if I want to take the derivative of this last one, I'm going to do low d high minus high d low all over low squared. So my low function, first, low. So that's sine of x plus cosine x. Now, d high. D high would be 1. Minus. You notice how I put both low and d high in parentheses. I think that's a really, really good idea. When you have more than one term for your low or your high, those parentheses come extremely important. And remember, AP will grade whatever you write. So if you write it without the parentheses, then technically it's not the same thing. So please put everything in parentheses. So low d high minus. Now we have high. There's high. Now d low. D low we actually did in the first step. So isn't it just cosine of x minus sine of x? All right, so that's low d high minus high d low all over. And now we have low squared. Generally, you want to go ahead and just simplify the numerator. That's the general practice as far as multiple, because these are usually multiple choice. So I'm going to go ahead and simplify the numerator a little bit and see what I can do. Okay, first thing I did is distribute my 1. Now I'm going to distribute my x, and I'm going to go ahead and distribute that negative that's right there too. So I have negative x cosine x, and then this becomes plus x sine of x. And then it's all over sine of x plus cosine of x quantity squared. All right, so I look at that and I say, well, can I simplify that? I suppose I could try factor by grouping at the top, but if I do try factor by grouping, it will not simplify anymore, so I'm going to leave that one alone. When you're doing your problems on your assignment tonight, I want you to check all of your odds and look at the back, and if your answer doesn't look the same, see if it's wrong or see if they just simplified it. Maybe they simplified it farther than you did, okay? And if it's even, I would just simplify it as far as you go, and we'll check it when we check over the assignments. Okay. Couple simple definitions. This will not be something you have to memorize. It is simple harmonic motion. That is motion moving with uniform speed around the circumference, or motion of a particle moving in a straight line. You can probably see why this is in this section. If I were to move in uniform speed around the circumference, isn't that like going around the unit circle, and we had to memorize that unit circle? And you know how when we graphed the unit circle on an XY plane, that ended up being sine and cosine? So that's why it's in here. And then another thing that I think I've mentioned to you before, but we haven't necessarily put in our notes, and that is jerk. What a jerk is it's the derivative or the rate of change of acceleration. So it's actually the third derivative. All right, and some of you that have learned to drive recently know exactly what a jerk is in the car. Some of you that have had a date that didn't work out very well know what a jerk is outside of the car. All right, so let's take a look at this. More derivatives. More derivatives you have to memorize. This is a great time to go into Quizlet and make a little cards or just get note cards and get these memorized. Derivative of tangent is secant squared, and derivative of cotangent is negative cosecant squared of x. Okay, so let's say them out loud again. I want to say derivative of whatever, and you're going to tell me what its derivative is. The derivative of tangent is? What? I didn't hear you. The derivative of tangent is? Awesome. And what's the derivative of cotangent? Derivative of cotangent? Close your eyes. The derivative of cotangent? Good. Negative cosecant squared. So, why? Why isn't this as simple as the last one? Let me show you where these come from. I'm going to show you the proof of this one because I think it's kind of cool. You don't have to know how to do the proof. You don't need to memorize the proof. I'm just showing you the proof so that you understand why this derivative is what it is. If I wanted to show you the derivative of tan of x, isn't tan of x the same as sine of x over cosine x? True. Now, if I were to take the derivative of sine of x over cosine x, aren't I going to need quotient rule? So here I go with the derivative. I'm going to say low d high minus high d low all over low squared. Okay, let's see what happens when I simplify this. Cosine times cosine is cosine squared. A negative times a negative is positive. Sine times sine is sine squared. And whoa, I hope you're seeing an identity. Oh yeah, I remember that sine squared plus cosine squared is 1. And what's 1 over cosine squared? You got it, secant squared. So what we just saw is that the derivative of tangent equals secant squared. Another way you can remember tan and secant, they're kind of partners. They're kind of a thing. They like hook up. Okay, and I know having a thing is something that older people don't really understand, but apparently it's something to you. And hooking up probably means something entirely differently than what I'm talking about here. But tangent and secant kind of go together. You remember Pythagorean theorem? Yeah, now do you remember the Pythagorean identities that we had in pre-calc? 1 plus tangent squared equals secant squared. And 1 plus cotangent squared equals cosecant squared. So the cos already went together, and the tan and secant went together. So, you know, I don't know, maybe you can remember that way, or you can remember that the cos go together or something. All right, now the proof for cotangent works exactly the same, only cosine's on top and sine's on the bottom, and you can imagine because of sines and because of quotient rule has a negative in there that the signs end up working just out, they work out exactly the opposite. All right, so I'm going to ask one more time. All right, here we go. Now listen, I want you to say it out loud. All right, whoever, if you hear your partner not saying anything, you have my permission to kick them in the shin. Okay, so right now, get your feet ready to kick your partner. So partner, you better speak up. Now listen before you answer. What's the derivative of sine? Cosine. Good. What's the derivative of tan? Secant squared. All right. What's the derivative of cosine? Did you get the negative on there? Negative sine of x. Great. And what's the derivative of cotangent? Negative cosecant squared. All right. We're just going to need to start memorizing those. Here's 2 more. So you you see this one's not quite as obvious either. The derivative of secant of x is secant x tangent x, and the derivative of cosecant x is negative, of course, cosecant x cotangent. You know, it's kind of the same. Secant and tangent still go together, and cotangent and cosecant still go together. So, I don't know, maybe you can remember it like that. I'm going to show you the proof for secant. And I'm going to use quotient rule again. Let's see, if I wanted to take the derivative of secant of x, that's the same as taking the derivative of 1 over cosine x, because isn't secant 1 over cosine? All right, I'm going to need to use quotient rule again. So the derivative of 1 over cosine is low, d high would be 0, wouldn't it? Minus high, d low would be negative sine of x, all over low squared. All right, let's see what happens. 0, so that goes away, and negative times a negative is positive. So I have a sine of x over cosine squared. And is it okay for cosine squared if I write cosine times cosine? Would that be okay? And for sine of x, is it okay if I wrote sine of x times 1? Well, what you notice right here is, guess who that is? Sine over cosine. Yeah, you got it. That's tan. And what's 1 over cosine? That's secant. And so you see how that derivative ends up working out. It's so cool how that works. Not as cool as you, but pretty cool. All right, so here we go with an example. Find the points on the curve y equals tan of x from negative pi halves to pi halves, where the tangent is parallel to y equals 2x. All right, so I'm going to go through this step by step, and I'm going to model what I would think and do if I were doing this problem. First of all, the problem says find the points. Find the points. So my answer is going to be in some kind of point. I don't know how many points. I just don't know. But I know my answer is going to look like a point. Find the points. All right, got it. On the curve, y equals tan of x. Okay. Where the tangent? Tangent. What does tangent mean? Tangent line is the slope of instantaneous rate of change. So I know tangent means derivative. So I'm going to have to find derivative. Tangent means derivative. Now I know it doesn't say tangent line, but it doesn't really matter because I'm going to answer in a point anyway. So I know tangent means derivative. Okay, let's keep reading. Is parallel to y equals 2x. What does parallel to y equals 2x mean? Parallel to y equals 2x means it has the same slope as y equals 2x, which means our slope has to equal 2. Well, that's interesting because isn't tangent also slope or derivative? So, holy cow, doesn't that mean that the derivative has to equal 2? The derivative of what? Our function. So, let's find the derivative. The derivative of tan is secant squared of x. And what we're saying on this problem is that the derivative, the tangent, has to be parallel to 2x. Y equals 2x. So that means it has to be parallel to 2x. So that means it has a slope of 2. Does that make sense? All right. So now, a lot of the rest of the problems we do today are going to be just trig stuff. It's going to be reminding you about some trig things that you need to know. How in the world am I going to solve secant squared x equals 2? Well, let's see. I want to know what x equals. That's my job. So I got to get rid of secant, and I got to get rid of a square. I know how to get rid of squares. How I get rid of squares is that I square root them. And when I square root them, I always plus or minus. All right, so there's one step. So I know that secant of x equals plus or minus square root of 2. Now, some of you may have this one memorized already. I don't. I don't have secants memorized. I have sine and cosines memorized. So here's what I'm going to do. I don't like secant. He is not my buddy. Cosine is my buddy. So I'm going to turn secant into cosine. If secant of x equals plus or minus square root of 2, if I do 1 over both sides, isn't that fair? So if I do 1 over secant, isn't that cosine? And what's 1 over the square root of 2? 1 over the square root of 2, if I rationalize, doesn't that end up being the square root of 2 over 2? And now I am a happy camper. Why am I a happy camper? Because I know this. This is from my unit circle. Where is cosine equal to the square root of 2 over 2? There's 2 spots. It's either equal to it in all of the pi fourths locations. But because of this right here, we only want the answers between negative pi halves and pi halves. So that means the places where cosine is plus or minus square root of 2 over 2 are negative pi fourths and pi fourths. Yay! I know my x. Yay. And if I know my x, how do I always get my y? I plug it in. Y equals tan of x. So in this case, y equals the tan of pi force. The tan of pi force is 1, and the tan of negative pi force is -1, and I have now answered the question. Those are what points where the slope or the derivative of y equals tan of x has a slope of 2. Okay? All right, next problem. Get your books out and open to section 3.5, problem number 22. All right, we are going to have a fair amount of trig review for this question. So the first thing that I want to do is I'm going to just draw the picture up that's in the book. It looks a little something like this, where this is Q, and I believe that's a horizontal tangent. And then they have a point P, which if I remember correctly is pi fourths 4. Okay, I'm going to be honest with you. I don't have a book with me right now, but I'm pretty sure that's what the point is. So if I'm screwing it up, I'm really sorry. I don't want to screw it up, but I'm pretty sure that's what it is. All right, so this is what's given to us. Oh, hang on. I am definitely going to need this book because I need the equation. So you're going to pause for a minute, and I'm going to go get the book. Okay, well, the good news is I was right on that stuff. So now the equation of this line that is up here is y equals 1 plus the square root of 2 cosecant x plus cotangent of x. All right, that's apparently what that curve is. So the first piece of direction says find the tangent to the curve at P. Find the tangent to this curve at P. So we just want to find the tangent line. And so for the tangent line, we know we're going to have y minus y1 equals mx minus x1, because we want to do it at P. So all I need to figure out is what the m is. And the m is just the slope. So for part A here, m is going to be the derivative. Of course, I want to find it at pi force 4. But what would the derivative be? Let's see. I'm going back here to my y equals, and the derivative of 1 plus would be 0. The derivative of the square root of 2 cosecant. Oh gosh, get your notes. Get your notes. What's the derivative of cosecant? The derivative of cosecant is negative cosecant cotangent. Is it okay if I put that negative out front? And now the derivative of cotangent is negative cosecant squared. All right, so there's the derivative, and we want to find the derivative at pi force 4. So let's see if I can put all this in here. Negative square root of 2 cosecant of pi force cotangent of pi force minus cosecant squared of pi force. Now, these are not ones I've memorized, so I'm going to show you what I do. I'm going to come over here and draw pi force, and I know that it goes like this. Cosine, sine, tangent. This is cosine, sine, and tangent. You notice how all of these are the reciprocal functions. So what happens if you flip over the square root of 2 over 2? You get this, right? And if you rationalize, do you see how you're going to get the square root of 2 if you flip it over? So flipped over, there are all my values. I love flipping over 1 because you get 1. So let's see if I can figure out what this is here. I have negative square root of 2. What's the cosecant of pi force? Okay, that's square root of 2. What's cotangent of pi force? 1. And then Cosecant of pi fourths is square root of 2, but I'm going to square it. So I end up with negative square root of 2 times the square root of 2 is 2, minus the square root of 2 squared is 2, and so I get negative 4. Boom, there's my slope. Okay, that's part A. That is part A. Now, if you look at part B, it says, well, what is the horizontal tangent at Q? So if I go to Q, I'm like, okay, Q is at the point, oh crap, I don't know. What do I know though at Q? I know that there's a horizontal tangent there. So what do I know about its slope? You got it, it's 0. So for this answer, I know it's going to be y minus something equals 0, x minus something. I really don't even care what this is because when I take 0 and distribute it, I'm going to get everything. So I really need to know that y one. Gosh, I need to know that y one. How do I do this? All I know is that the slope is 0. That's all I know. But I know slope is derivative. So I could, on part B, just say that the derivative equals 0. What I just wrote right now is actually really important. On an AP free response question, there are always 9 points for each question. There's 6 free response questions that each have 9 points each. Sometimes just simply setting the derivative equal to 0 and writing that on your paper gains you 1 point. Okay, so you don't even have to do the math. They just want to see, hey, they knew to set their derivative equal to 0. So sometimes that's worth a point. So I made sure to write that down. So the derivative equals 0. And what is the derivative? Let's see, I found it earlier. Negative square root of 2 cosecant x cotangent x minus cosecant squared x. So I want this to equal 0. Oh my gosh, how am I supposed to find out what x equals here? This is going to be quite the trig problem. So I look at this and I say, man, I see a couple things that I could do. I could factor out a cosecant, couldn't I? I could factor out a cosecant. What else could I do? I could put everything in terms of sine and cosine. That's always a strategy. Factoring seems a little easier. So I'm going to go ahead and try to solve this. So I'm going to go ahead and factor out a cosecant of x. Okay. So this equals 0. I'm going to use zero product property. Here's what zero product property says. You use it all the time. If I have two things that are multiplied together and equal 0, okay, smiley face times star equals 0, then I set each one of them equal to 0. Because if something times something equals 0, if either one of them is 0, that'll work. So what I'm going to do is I'm going to set cosecant of x equal to 0, and I'm going to set negative square root of 2 cotangent of x minus cosecant of x equal to 0. Whew, that is a mouthful. Okay, let's come over here. This guy right here. Where is cosecant of x equal to 0? I can't really do 1 over because 1 over cosecant is sine and 1 over 0 is undefined. Is sine undefined anywhere? No. Can you guys think of the graph of cosecant of x? Think. Doesn't it look like this? Remember where there's the x-axis kind of in between them? Where does cosecant of x equal 0? You're right. It never ever does. This never equals 0, so that's out. So where does this happen? Oh gosh, I have no idea on this right here. When I get stuck, sometimes what I try to do is put everything in terms of sine and cosine because they're the bomb. So I'm going to go ahead and write cotangent as, cotangent is cosine of x over sine of x. And then cosecant is 1 over sine of x. Okay, I'm getting there. You know what I notice? Hey, both of them have sine in the bottom, so I can write them as one fraction. I can put them together. So I have negative square root of 2 cosine of x minus 1 equals 0. What does this say? It says negative square root of 2 cosine x minus 1 over sine of x. You know, it says a fraction equals 0, right? Isn't that what it really says? Some fraction, crazy, equals 0. Crazy fraction equals 0. How can a fraction equal 0? The only way a fraction can equal 0 is if the top is 0. The bottom can't be 0, that's no good. But if the top equals 0, that's what'll work. So I'm going to go ahead and say, I'm going to come up here, I'm going to go ahead and say that the numerator, which is this negative square root of 2, cosine of x minus 1 has to equal 0. And now, whoo, I am there. I'm going to add my 1 to both sides and divide, and I get, oh, I'm going to rationalize my denominator. Yay! I get cosine of x equal to negative square root of 2 over 2, and that's one I know on my unit circle. Doesn't that happen like here and here? Yeah, and looking at the graph, it's probably this first one that they want, so that's 3 pi fourths. So I'm getting there. Gosh, what the heck was I doing? Oh yeah, this graph way up here, it's 3 pi fourths. So that right here is 3 pi fourths. But don't I really need this y1 right here? Don't I really need the y1? So how do I get the y if I have the x? You're right, I plug it in, and I got to plug it into the original. I don't want to know what y prime is, I want to know what y equals. So where is y? Oh gosh, way up here. So I'm going to plug it in. 1 plus square root of 2 cosecant, not of x, but of 3 pi fourths, plus cotangent of 3 pi fourths. Now I'm using my unit circle right there, 3 pi fourths. What's the cosecant of 3 pi fourths going to be? Well, the sine is positive, so cosecant is positive, so it's square root of 2. And then the cotangent of 3 pi fourths is going to be negative 1. So what do we get? 1 plus 2 minus 1, so we get 2. So that is my y value right here. So my equation is really just y equals 2. Whoa, that was long. Will you have something like this? Yeah, you might. You probably won't have 6 of them, but yes, you will. Okay, we're almost done. This problem, it's a good thing we got lots of board space. Well, I don't know if we have enough board space in here. We want to know the 725th derivative of sine. All right, this shouldn't take too long. Let's see, how many of you are there in here? 20. So if you each do like what? I don't know. 20, what's 800 divided by 20 is like 40. So yeah, if we each do like 40 derivatives, we can get there. So okay, so let's just look at this. We're starting with sine. That's what y equals. And then we have first derivative, and that's going to be the derivative of sine is cosine. And then we want the second derivative, and the derivative of cosine is negative sine. And now we want the third derivative, and that is, let's see, the derivative of sine is cosine, so the derivative of negative sine is negative cosine. All right, now the fourth derivative, and that's going to be the derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. Oh, hey, look. Are we going to start over? It's just going to keep repeating itself. So there's really just 4 that repeat. What does this remind you of? I, right? Didn't I repeat I squared, I cubed, I did the fourth, and then it started over? So, how did your teachers show you to do like I to the 725th? What did they do? Since it cycles every 4, let's take 725 and divide by 4. Let's do that. We would get 7, 8, 1. That's what we would get. Okay, if we take 725 and we divide by 4, we get 181, but we have 1 left over. And what that 1 left over is it tells you which derivative we're on. So for example, I'm going to do one that's a little smaller. If I were to just say, fine, I'm going to come back over here. Come back over here. So this would also be, this is the first derivative, but isn't it also the 5th derivative, and this is the 6th derivative, and this is the 7th derivative, and this is the 8th derivative, and then this is the 9th derivative, and then this is the 10th derivative, and this is the 11th, and this is the 12th? 4, 5. Yeah, that's right. And so if you notice, what's 5 divided by 4? 1 with a remainder of 1. What's 6 divided by 4? 1 with a remainder of 2. Do you see how your remainder is matching up to your original? Really, 4 is the same as 0. It's the same because this is like the 0th one. And so if you notice, whatever your remainder is, it matches up with here. So since we have a remainder of 1, this is the same as the first derivative of sine, which is cosine of x. Okay? Or you could do it 725 times. All right. Here is your assignment. It will take you a little bit, so get started. Don't be messing around. You've got lots and lots of time. I'm trying here. Trying to get this because I want you to see this amazing picture of Bart Simpson being barbecued by his family or being melted. It will take you a little while. Your biggest struggle is going to be simplifying and figuring out how if the answer in the back of the book is the same as yours. So please make sure and check your odds. We will go over these tomorrow. I hope you have a fabulous day.